presented by Caltech.
Recap of the last thing we did. We're using this mass and a spring with this magnetic eddy current damping as our prototypical system to talk about harmonic oscillators, the given harmonic oscillator here. So we've derived all of these results here, so I just wrote it down. So the full solution for the steady state motion is given there with these assumptions. If I pick out the amplitude piece, I get this. And the phase that appears in there, the delta of omega, as a function of omega, is this inverse tangent. So that's just to remind you where we ended up. This amplitude, I drew a sketch last time, but I will make a better graph of it here. For three different cases. So it's a graph of the amplitude as a function of the frequency. It's a graph for little a equals to 1, so the driving motion is magnitude 1 in whatever units you want, centimeters or miles or light years, whatever. And the damping is also taken to be 1. So it's a 1 inverse second or inverse year or whatever. Specify what units I'm using, it's just 1 of whatever units I'm using. And then for the blue curve, this is light damping where I've taken omega naught to be pi. So the Q value is about 3. Q value is pi. And this is the shape that you get for A of omega. Now, one thing to notice is that in all three cases, whatever the case is, the amplitude is going to 1 at 0 frequency. That's A equals 1, so they're approaching A at omega equals 0, little a. We demonstrated that last time for different cases, that that's what we expect. In the limit of the 0 frequency, the amplitude of your motion is the same as the driving force. The driving force, the amplitude, whatever. For the case of light damping, you see you get a resonance curve, what we call a resonance curve. That peaks at, well, what's it peak at? It peaks at whatever we derived at omega naught, roughly. And if I increase the damping to critical damping, I get the red curve. And if I increase the damping still further, and I'm increasing the damping by just decreasing the frequency. So the critical damping, I'm letting the frequency be given by gamma over 2. That's the critical damping criterion. So omega naught is 0.5 here. Or omega naught. Where? Here. And cursed. Okay. So critical damping there, omega naught is gamma over 2, or just 1/2. And down here I've gone down to omega naught of 0.3 for heavy damping. So you see, in the resonance case you get a peak, in the light damping case rather you get a peak, and when you get past critical damping, the peak is all the way down at frequency 0. Yeah.
Maybe I'm just mistaken, but I thought that critical damping was the one that returns equilibrium distance.
This is the frequency response, not the time dependence. Yeah, actually I should have said that. You're exactly right. But in terms of the frequency response, it's kind of the border line between sort of the light damping and the heavier damping. Okay, any other questions on this? So I want to go on now and discuss the energy dissipation in this system. Because of course it's of interest to know how fast you're spending your energy these days. And the point here is that the energy is being dissipated in whatever the damping mechanism is. That's where the energy is getting lost. Of course, we're in steady state motion, so we keep providing the energy back to the system to keep it in steady state. So the driving force is putting energy into the system, and the dissipation is taking energy out of the system at the same rate. Okay, we're taking it out just as fast as we're putting it in, or vice versa. So let's assume, for the sake of our discussion, that we're lightly damped. We could go ahead and analyze in other situations too if we wanted to. So the rate of energy dissipation is just the power that's dissipated. Okay. So this is equal to the power needed to maintain a steady state motion. And dissipation is in the damping mechanism. So those two must be equal. So let's see. Power. Function of time, in general. Was just the rate of change in energy. So what is that? Energy is a force through a distance, if we're talking about a force. And then taking that over the time in which you're doing it gives you the power. Okay. So the force is the dissipative force. And so the force times the distance is there, and the rate of change with time is given by dividing by t. So what is this? Well, the dissipative force is our velocity-dependent force, gamma m v dot, so this was what we called F sub v before. And dx by dt is just the speed, okay, just the velocity. So that is not v dot. Yeah, v, which is x dot, sorry, and times dx by dt, which is another x dot. So this is just gamma m x dot squared. So we know what x is, so we can figure out what x dot is by taking the derivative. So if x of t is our amplitude factor times a cosine of, well, let's write it, sorry, I was going to write it using exponentials. Let's do that. know, I want to get some practice with this. So that's x. Of course, you take the real part and you get cosine omega t minus delta there. But we don't have to do that yet. Let's just take the derivative to get x, the velocity. So we pull down an I omega, and then we have exponential e to the I omega t minus delta. I can make the real part now. So that's equal to minus a omega, because the real part's going to be in the I sine omega t minus delta. So I squared is minus 1 times omega times sine omega t minus delta. Okay. So I have x dot, I can calculate the power now. All right. E of t. I'll write it, I'll keep in mind that it's at frequency omega. So the power that's getting dissipated is going to be a function of frequency. So let me keep that in there. So gamma m, so it's the gamma m, and then I have to square this. So let's bring out omega squared, a of omega squared, of course minus 1 squared is just 1, sine squared omega t minus delta. So that's the answer. It's actually usually more interesting to speak of the time averaged power. We're in steady state, so averaging out the individual cycles, we get some average rate of power dissipation. So let's do that. So we have to integrate. This over one cycle of motion to get an average. So, I mean, I could do n cycles, but we just want to get the average over some number of cycles. So we have to do the integral from 0 to the period t of sine squared omega t minus delta dt. So we notice that, well, we could just let theta be whatever is in here and do the corresponding manipulations. It's basically just an average of sine squared theta over one cycle. That's all it is. Okay? So the average of sine squared over one cycle d theta, well, that's just going to be half of the average of sine squared plus cosine squared, which is 1, so it's 1/2 the average of 1 over a cycle, which is just equal to 1/2. So now we have, so let me call the average, let me call that a P with a bar over it to indicate an average. Okay. So let's see. So I get a half from doing this integral. I have a gamma m omega squared. And I have an a of omega squared. That's my time average power. So the rate, on the average, the rate of energy being dissipated in my eddy currents or an LCR circuit is the average rate of energy loss that's dissipated in the resistor. Okay, so let's look at this a little bit. Just to try to understand it a little better. So let's plug in what A is. So E squared omega squared, and then this is I squared. So I'm just squaring the expression over there. Omega squared squared, try to get it in the right place, plus omega squared gamma squared. So you can check my units as you go along, make sure that I'm not making any mistakes. Hopefully I'm not. This part here is dimensionless. That's nice. I'm going to rewrite this, extracting the part that I'm really interested in, which is the frequency dependence. So gamma m a squared, I'm going to pull out an omega naught squared, and I'm going to describe the rest of it as g of omega. So g of omega is omega squared, omega naught squared. So I've taken this omega squared and replaced one of the omega naught squares in here to make it look like this. It pulled off the omega naught squared over here. I haven't lost anything. So G is a dimensionless function of frequency. When it gives the frequency dependence of my steady state power loss. So again, I could ask questions like, well, so obviously this has some shape to it as a function of frequency. If I make a graph like the one I showed, I'll have some shape as a function of frequency. I'm lightly damped, so in fact it will have some peak in it. And I can ask where it's maximum. So, here's the maximum. Well, it's maximal when take the derivative d by d omega of g of omega, but let me take the derivative of, so let me divide through by this omega naught squared, since I don't like it there. It's not a function of omega. And I'll take 1 over it, which will be easier to find the derivative equal to 0. So I'm going to take the derivative of omega naught squared. I mean, this is just technical, trying to make my life easier. You could just go ahead and take the derivative of this percent equal to 0, and that's fine. I'm just trying to save myself some effort. See, if I flip this around, then I get this complicated stuff on top, and I can divide through by omega squared, and this just becomes a constant. I get rid of that, and the derivative is actually quite easy to do. So that's just that. So here we find that the peak is actually, well, okay, I mean, it's a quartic equation in the frequency that I'm saying equal to 0. So there are 4 roots to this equation. The roots are omega is equal to plus or minus omega naught and plus or minus I omega naught. Only one of those is a physical frequency, so that's the one I'm going to use. So the maximum of my power occurs at omega equals omega naught. So we find that the power dissipation of the oscillator actually has its peak at the natural frequency of the oscillator. The power dissipation. So at omega equals omega naught, so at the maximum, we get G is just equal to whatever G was, so we'll be able to make it to the fourth divided by gamma squared, omega squared, omega naught squared. So this becomes omega naught over gamma squared. And so therefore, the maximum power is at the frequency omega naught again, is equal to 1/2 gamma m a squared omega naught squared times omega naught over gamma squared. See that? So I can rewrite this. Yeah, it looks a little complicated. It has both gamma and omega naught, but if I remember that omega naught over gamma is just Q, that gets that part out. But then I can deal with this part too by remembering that, well, let's see, I can do it this way. Gamma is just what? It's omega naught over Q. And so this is equal to, I'll do it in this order, 1/2 ma squared omega naught cubed, that doesn't look much simpler, times Q. But now I just can remember that omega naught squared is K over M, and describe this in terms of K, 1/2 K A squared, which looks like in energy in a spring, times omega naught Q. Yeah, okay, this. Maybe a nice way to write it. Of course, you write it whatever way you need to have, whatever variables you need. Let's go a little bit further. So we say this is, some curve, it got a peak, it goes down. How wide is this curve? It's again a resonance curve, and you want to know how sharp that resonance is. We expect the sharpness of the resonance to have something to do with Q, but let's see how it works. Let's ask the question, to get at the width of this resonance curve, let's ask where it decreases by 1/2 from its maximum. So I'm going after the full width at half max of my frequency response. So let's see, so that happens at, I'll take 1 over A again, because, see, there's my power there. I want that to be 1/2 of the maximum. But if I take 1 over it, it's going to be 2 times 1 over the maximum. Okay, so let's just do it. It's just technical, trying to make my life easier. You don't have to do it this way. So this is 1 over G of omega. And that, if I divide this by 1 over G max, that is multiplied by omega naught over gamma squared I want to find that frequency where this is equal to 2. Okay, well, so what does this give us? It gives us omega naught squared minus omega squared plus omega squared gamma squared. Let's see, so this is, so multiplied through by this, and I have 2, so I have to divide that out there, so I get 2 omega squared gamma squared, or put this on the other side and multiply through by omega squared, omega naught squared. So I've got, let's see, got the square. Okay. Got the square. Check of units, okay. So let's see, so I have basically a quadratic equation in omega squared, and so I can solve that. So actually, this is easy because I can just notice that this is omega naught squared minus omega squared, omega naught squared minus omega squared. If I take, because this is just this is equal to plus or minus omega gamma. So I move this over to the other side, got rid of the 2, and taking the square root of both sides. So if we solve this quadratic equation, easy one to solve, I get omega is just equal to omega naught times 1 plus 1 over 4 q squared plus or minus gamma over 2. So I've used the fact that the q is omega naught over gamma in doing this. If we're really lightly damped, that is, if q is much bigger than 1, then this kind of disappears, and we get omega naught plus or minus gamma over 2 for my solutions where my power dissipation decreases by 1/2 from its maximum. So let me just draw a graph of it. Yeah.
Can you explain again why we're looking for g of omega equals 1/2 g max?
So g of omega is effectively my time average power, and I found out. I just want to characterize the curve, the frequency response curve of my power dissipation. And so one characteristic is where it peaks. Another characteristic is how wide this is. That is how if I go away from the resonant frequency, how wide is the distribution where I'm still dissipating a lot of power? You know, at some point when I go away, I'm not dissipating much power anymore. So how narrow do I have to set the frequency to hit that sweet spot of the resonance? And if it's an RF cavity, it's extremely important how wide that peak is. Because you want to, RF cavities, you may know, are often used to accelerate beams of particles. Those are protons. Provide an accelerating voltage. And you want to transfer that energy as efficiently as possible to the particles. And the higher the Q value, the more efficiently you're going to transfer the power because you operate it at the natural frequency, at the resonant frequency, where the particles act like the damping mechanism here, because you transfer the energy to the particles as you accelerate them. And so you want to dissipate that power as effectively as you want, and so you want very high Q values, and you don't want to. So you want the power frequency response to be very narrow. And so this is just a figure of merit that we're kind of deriving here. So let's see. I don't know if that really answered the question or not.
I think what I realized after you answered it was that the strategy is to find the values of omega at 1/2. Like there's going to be more than one value of
Right.
omega 1/2, and then you'll know the width.
Yeah, right. It's going to go down on both sides from the peak, and so I'm about to draw it. Okay. So we got a graph that looks kind of like this. So my time average power dissipation as a function of frequency, it's going to look, so G of omega, it goes to 0 at omega equals 0. So if the driving frequency goes to 0, I should approach 0. And as omega goes to infinity, it should also go to 0. Yeah.
What does like G of omega like physically represent?
It is, down where you can see it. So I've just written out the power. All the G of omega is this piece of it. So there's some constant in front of the G of omega. But basically, G of omega describes the power that's being distributed. It's being dissipated. It's proportional to the power dissipated. I could use power itself instead of G of omega, but I just didn't want to deal with extra constants. Right, because I defined, well, up to, here's what it is. The power is this constant times G of omega. Okay? And so I'm just using G of omega instead of power itself. But but okay, so here I'll put the, so this is 1/2 ELF m squared omega naught squared G of omega. So this is what I'm plotting here. So is that okay? Is that?
Thank you.
Yeah, okay. So I start at 0. It goes to 0 at 0 frequency. It reaches some peak and tails off to 0 again at high frequencies. The peak we derived is at omega naught. So this is P max as a function. So that's at omega max, at omega naught, it's the maximum. Is half of P max at these points. And these points are omega naught minus gamma over 2 and omega naught plus gamma over 2. Those are the frequencies. And so this full width at half max is just equal to gamma. You know, this minus this is just gamma. Yeah.
This is only for the case of light damping.
This is light damping. Yeah, so, and in particular, this is very light damping where Q is much bigger than 1, where this relation holds and the distribution becomes approximately symmetric. Okay, so that's damped-driven harmonic oscillators. Are there any nagging worries? Because I'm gonna go on, I'm gonna still do this, but I'm gonna make things a little more interesting now. Yeah, oh, sorry.
What then did the acronym FWHM stand for?
Sorry. Full width at half maximum. Full width at half maximum. Okay. You'll see HWHM too for half width at half maximum. Sorry. Too much jargon. Okay, so let's make things a little more interesting. I did a demo with these two tennis balls. They had a little spring between them, and so the motion of one tennis ball wasn't really independent of the motion of the other. So that raises the subject of coupling oscillators together. The coupled oscillations, okay? So let's consider a particular, just as we picked a particular system to discuss so far with the spring mass on a string, let me consider a particular mechanical system to guide our thought. But it's a really generalizes to the other kinds of situations that we've been thinking about. Let's consider a mechanical system. Again, a little bit different. It'd be a little bit like my tennis balls, except not quite the same. I'm going to have two pendulums, mass M, length L, and I'm going to put a spring between them with spring constant K. And again, I'm faced with trying to decide coordinate systems. Let me first think about Cartesian coordinate system, because that's somehow the first thing we do. Okay. So I'm going to define the x direction to be this direction. This XB and XA, so XA is the one to the right, of course you can do it this way. So this is to be considered mass B, and this is to be considered mass A. And then the corresponding Y's, YA and YB, are in the other direction. With origin chosen somewhere. So I'm going to, I'll choose the origins at the equilibrium positions of the two masses. That seems like the obvious thing to do. So I'm assuming that the length is rigid, so that it doesn't bounce up and down or something. All it does is swing in one direction. I'm assuming it doesn't swing in the other direction, which was what the tennis balls did. They went the other direction. I'm assuming that they only can swing in the plane of the board. So if I take mass A, pull it out here, and let go, with B initially at rest, we can probably guess that what's going to happen is that A will push on this spring, and then I'll push on yeah.
But if they're the same mass, there'll be different masses.
I'm assuming they're the same mass here. We could analyze with different masses. It'd just be a little more complicated, but it wouldn't be too much harder. So the initial motion of mass A is going to transmit through the spring to mass B, and pretty soon mass B is going to start oscillating. And it's probably going to slosh back and forth between the two. The motion is probably going to slosh back and forth between the two, just like we saw when I did the tennis balls. But let's see what happens. So I need to worry a little bit about making my life simple about these coordinate systems, what coordinates are important, which ones aren't important. I'm going to analyze this in the limit of small motions again. So let's think about that. So if I take and draw this out, so I'm going to suppose that I've got, so let's concentrate on mass A for the time being. So I'm going to let the angle that it makes to the vertical, to the equilibrium position, be theta sub A. And the lengths are L in both cases, so it's length from there to up there. So the coordinates here are going to be y sub A and y c. This distance here is y sub A, if you like, and this distance here is x sub A. Okay, well x sub A is just equal to L times tangent of theta sub A. Here's x sub A there. And there's y sub A there. Okay? So x sub A is just given by L tan theta sub A. Y sub A we actually figured out before when we talked about the single pendulum. But you can see it again, so this is L minus, so L is, what am I trying to say? It's 1 minus, so proportional L, but it's 1 minus cosine theta sub A. Okay. So let's see. If I consider small angles, so small motion, then x sub A is approximately L times theta sub A, since the tangent for small angles is about the same as the angle. And y sub A is approximately L times, well, cosine theta goes, if you take the Taylor series expansion for cosine theta A, it goes like 1 plus theta squared over 2 plus 4 factorial and so forth. And so if we keep the 1 will cancel this 1, and so we're left with the theta squared. Theta sub A squared over 2. So for small angles, I can safely neglect y sub A compared to x sub A. So I'm going to be thinking about the x coordinate here. So remember, for uncoupled motion, we solved that problem. We had that theta sub A double dot plus g over L times theta sub A was equal to 0. That was our differential equation. And the natural frequency was square root of g over L. Assuming no damping. So we're all the way back to no damping. So we're assuming no damping, just to make that explicit. Damping makes things interesting, and maybe we'll investigate that in homework a little bit or something. But we're going to assume that we have no damping. It's already interesting. So the natural frequency we had was omega naught equals square root of G over L. And the only force that we had, the only restoring force that we had was gravity. We only had a single, oscillator, single pendulum. So let's see if we can analyze what happens in general for this coupled motion. Okay, good. So I'm going to use x sub A and x sub B instead of theta A sub theta B. This will turn out to be both an intuitive choice and a pretty good choice. Okay. Because one of the reasons is because that spring is in the x direction, and that's introducing another force that's just along the x direction. And it's a good coordinate system to describe that force in. So, we're going to use x sub A and x sub B, and we're going to assume they're small. So let's see, the gravitational restoring force on mass I, so I is just equal to A or B. So I'm just going to describe, yeah.
Is x sub b the resultant motion of the pendulum because we pulled on A, or are we assuming they both got pulled the same amount?
X sub A and x sub B are two independent coordinates.
Okay.
So, I mean, these things could be out like that, they could be that, you know. So we're describing this position with x sub B and this position with x sub A, and they may have nothing to do with each other. Well, they do, and ultimately they're two independent degrees of freedom in the system. So the gravitational restoring force is minus mg theta sub I. So we derived this before, so I'm not going to do it again. Okay. The force goes like the component of the gravitational force. It's back towards the equilibrium position. And so if you take and do your vector diagram of forces, you find that the restoring force. So there's a force of mg down here, and then you have to take the component that's back here, and the component that's perpendicular to that, that is towards the attachment point. This will be mg times sine theta sub I, I guess. And I'm just taking the approximation that sine theta is approximately theta. All right. Okay, but I said I was going to work with x's, so let's translate this to x. We have somewhere over there that x is approximately L times theta, so we have minus mg over L x sub I. Okay. Let's see, the force, let me do this all in one go. Yeah. So now, I've got to worry about the spring, this complication of the spring. The force on mass A from the spring is just F sub A is equal to F sub spring A, I guess. It's just, well, the spring constant, it's a restoring force, and the magnitude is proportional to the length of the spring away from equilibrium. So X sub A minus X sub B. On mass B, due to the spring, it's F sub spring B is equal to, well, I can write minus K times the length again in the other direction, but that's just going to be K times XA minus XB. Switch it, so I would have minus said XB minus XA, I'd have a minus sign. Okay. The important feature to notice here is that if I add these two up, they get zero. There's no net force on this system. I don't have some other force pushing from out here. So we have the differential equations. Mx sub A double dot, so Newton's law is equal to the restoring forces, mg over L x sub A minus k x sub A minus x sub B, and mx sub B double dot is equal to minus mg over L x sub B plus k x sub A minus x sub B. Okay, we're making progress. Let's just do what we did before and rewrite this a little bit with all the terms on the same side and dividing through by m, just to get it in kind of a standard representation. But that's all we're doing, is just sort of technology. So x sub A double dot plus g over L x sub A plus k over m x sub A minus x sub B is equal to 0. And x sub B double dot plus g over L x sub B minus k over m x sub A minus x sub B is equal to 0. So that's it. All we have to do is solve for the motion is integrate twice and get x sub A and x sub B. Well, it's not quite so easy as it was before, unfortunately, because they're nice and linear differential equations, but they're coupled. So that makes things in life a little harder. We've got differential equations that have, you know, if I try to solve this one, I find out, oh, wait a minute, I need to know x sub b. If I try to solve this one, oh, wait a minute, I have to know what x sub a is. So that complicates life. They are linear at least. So we can write them in a matrix form. D squared by dx squared, by dt squared rather, dt squared, by dt squared of x sub a, x sub b, written as a vector, so I'm going to let x be this vector, plus m, where m is some matrix, a, x, b is equal to 0. So I'm writing the same equation as here, except that I am defining my matrix M to be, so I read off the terms here. So I get a G over L plus K over M times XA, G over L plus K over M times XA, I get a minus K over M times XB, I get a minus k over m times xa, and I get a g over l plus k over m times xb. And so I've just rewritten my coupled differential equations in the form of a matrix equation. Of course, I haven't done anything to solve it yet. I've just rewritten the equation. But I can use this now in a convenient and very powerful way. And so the idea is to first notice that this is a symmetric matrix, and hopefully for a real symmetric matrix, and hopefully from your linear algebra studies, you know that you can do a coordinate system that diagonalizes your matrix, such a matrix, using an orthogonal transformation that is basically just doing a rotation in 2 dimensions. And so all we have to do is find a rotation that diagonalizes this. That will decouple the equations. We can solve the 2 equations independently and then plug it back in for xa and xb if that's what we want. So that's the program. It brings us to eigenvalues and eigenvectors too, but that's for next time.